In this video, we're going to talk about the second derivative test. In class, we're going to cover the concavity part, so this is starting on page 125. So we're not really starting at the beginning of the notes, but we're starting towards the end, so kind of find where that is. So this is, of course, page 125, and we're going to go on to page 126 at the bottom. Now, we've been talking about the idea of using our first derivative to determine relative maxes, relative mins. So we have that process of finding the derivative, figuring out the critical values, setting up our number line, then of course making our conclusions from our number line. So that's our first derivative test. The second derivative test is also a way that we can actually find relative maxes and relative mins. So if all I'm really looking for is a relative max and relative min, the second derivative test is faster. Less work, less number line, all of that stuff. And what the second derivative test says, it says let f be a function such that f prime of c is equal to 0. So a critical value, c is in fact going to be a critical value in our problem. And the second derivative of f exists. So it has to be twice differentiable on an open interval containing c. So if we get a critical value from an undefined term, meaning our derivative failed to exist there, we would look at that value. This test would no longer apply. It only applies if, in fact, our first derivative existed. Okay, and it is differentiable again. It says if the second derivative is greater than 0, then f of c has to be a relative minimum. If f double prime of c is less than 0, then it has to be a relative maximum. So the fact that our second derivative is greater than 0, meaning it's going to be a min. Second derivative less than 0, meaning it's going to be a max. So it's kind of opposite there. So a little confusing, but the process for finding the min-max using the second derivative test is actually a lot faster. It always starts with figuring out what the critical value is. So the first example says given f of x equal 2, and it gives us our function. Use the second derivative test to find whether f has a local maximum or a local minimum at x equals -3. Justify your answer. Well, first I have to confirm that x equals -3 is in fact a critical value. So I need to get my derivative up here. So my first derivative, f prime of x equals, when we take our derivative, we get 2x squared plus x minus 15. And then really, if I'm just determining if this is a critical value, I don't really have to set equal to solve. I can simply plug in the -3, and if I get 0 in my first derivative, then of course it is a critical value. So I'm going to do that really quickly. So f prime of -3. We want to know, is this 0? So we get 18 plus a -3 minus 15, which in fact does equal 0. So it is a critical value, so it meets the first part of the criteria of the second derivative test. Second part of the second derivative test is to determine whether it's a min or a max using the second derivative. So I'm going to get the second derivative up here. And our second derivative is 4x plus 1. When I take -3 and plug it in, I'm really not looking for the value. I can calculate the value, but what I'm looking for is this term going to be positive or negative? So -12 plus 1 gives us -11, which is in fact less than 0. Okay. So here's my justification, the way I would answer this question. So I would need to say since f prime of -3 is 0, that's the first part of the criteria, and f double prime of -3 is less than 0. F has a max at x equals -3. And I could say by the second derivative test. And that's kind of how we use the second derivative to determine max and min. So the last example on there says use the second derivative test if possible to find the relative extrema of the function and justify our answer. So now it's not asking us about a specific point, it's asking us just to find the max and mins overall, kind of like we did yesterday and today in class. So again, I'm going to start with my idea of the critical value. So I'm going to take my derivative, set it equal to 0, and start solving. So I'm going to factor this. So I get what? Plus 2 and x minus 1, which means x is in fact negative 2 and x is in fact 1. Okay, so two critical values as a result. Now to determine if they're the max or the min. So the next thing I need for the second derivative test is, of course, the second derivative. So if I do that, I get 12x plus 6. Now I want to take both the negative 2 and the 1 and plug them in. So if I do, I'm going to start with the negative 2, so that gives us negative 24 plus 6, which will give us negative 18, which is in fact less than 0. And if I plug in a 1, I get 12 plus 6, which is a positive 18. It's a very symmetric graph, which is greater than 0. Okay, and what that means is that this, because it was less, is our maximum, and this, because it was greater, is our min. So then I would say, since, or actually let's not start with since because we're not actually answering the same type of question as above, but I would say f has a max at x equals negative 2, since, or because, let me be consistent in what we've been doing. Two things have to happen. F prime of negative 2 is 0, and f double prime of negative 2 is less than 0. And of course, by second derivative test. Then I would say f has a min at x equals 1, because, again, establish two things. F prime of 1 was equal to 0, and f double prime of 1 was greater than 0. And of course, let's state the second derivative test. Okay. That's kind of how we use the second derivative to find max and mins. Okay. Either way is okay. Choose the one that works best for you. In some cases, it's going to be faster to use the second derivative test. In some cases, if I'm looking for increase and decreasing, I want to stick to the first derivative test. Sometimes I can't do that in certain situations where I would be forced to use the second derivative test. Okay, so if you have any questions, come in and see me.